deep reactive ion etching is based on isotropic etching by SF6 gas. And it's also dependent, so that the etch rate of the silicon is dependent to the width, to the dimension of your mask, of your holes that you made. And you can clearly see here. One of the problem of deep reactive ion etching is notching effect. So basically we call this notching effect, and this is because of the fact that when you reach to the end of your basically silicon and you reach the oxide layer, which is your stopping layer, then charge are accumulated because it works as a capacitance, and because of the accumulated charge, the positive ions of the plasma are like diffracted through the negative parts and then start etching the silicon like this. There are different solutions to solve this problem. For example, because this is a plasma-based process, and if we reduce the frequency of the plasma, we give a bit of time to this capacitor to discharge, and it can enhance this effect. So in general, this section can be concluded by this picture that in general, bulk micromachining gives us different possibilities. For example, here is a picture of anisotropic etching of silicon by KOH probably, and because it is anisotropically etched, and this layer, these spotted layers on top, is like silicon nitride or oxide. So KOH has selectivity to etch, so KOH cannot react with these layers, and then it only etched the silicon. Basically, it under etched our active area or active elements, and we have like floating areas. So bulk micromachining gives us several possibilities, but it's not the only way of making MEMS. Here, I'd like to start with surface micromachining. In surface micromachining, we deposit layers, we etch them, we deposit pattern. So only with thin film sputtering, thin film deposition. So substrate doesn't play a very important role, if they say so, basically. But in my idea, it's not completely true, because when you do surface micromachining, you are playing with layers, you are depositing materials, and the quality, the properties of the material is directly dependent to the substrate. For example, if you deposit a metal like platinum on glass, it doesn't have same properties than the platinum deposited on silicon. So it's very important to take into account. But I don't go to details. Just keep in mind that substrate is still important, but not as mechanical, as a mechanical, let's say, device or part in our MEMS device. So in surface micromachining, we can realize our devices by this step. So it's a very simple image that explains the process. So we deposit a layer here. We call this sacrificial layer. So it can be polysilicon, it can be silicon oxide. I will let you know how you choose it. So it's a sacrificial layer, and then we deposit our active element. So it can be a beam, whatever. The thing that is like floating is going to move. We deposit there, and then afterwards we etch it. We etch the sacrificial layer, and this guy starts being floating. So this is surface micromachining. So we don't touch the substrate at all. So substrate is there just to support our device, our layers that were deposited. So yeah. I explained this. Limited geometrics possible. That's true, because you are dealing with thin films. So you cannot really go for thick materials, but still is possible with different techniques, which I will explain. In general, the advantage of surface micromachining is that it's very cheap compared to bulk micromachining. You don't need advanced like deep reactive ion etching stuff. Deep reactive ion etching machine costs about €1 million. So this kind of stuff for bulk micromachining is very expensive. But for surface micromachining is very cheap. And so this is also another example, real picture of surface micromachining. So this is a sacrificial layer deposited, and we have the device on top, and then we pattern it. So you can see a membrane, a floating membrane, and here is like the gap. It can be vacuum or air. One of the examples of surface micromachining is this picture, which is a motor, MEMS motor, micromotor, which can be actuated by electrostatic forces. So basically, this motor, this guy here, is floating somehow, and this is the stator. And the stator, we connect it to 3 phases. So basically, there are 12 of these guys, and we actuate them with pulses, with a square wave, but with 3 phases. So three different basically signal generator you need or whatever, and then it causes this motor to rotate. Another picture of this guy. So you can see that this is floating. So this is the motor and this is the stator. This is not the stator. This is a shaft, I think. This is the shaft to this part in the center, and this is the stator. But how do we fabricate such a thing? So to go a bit more, you don't have this slide I added to make it a bit more clear. So here we start with our sacrificial layer, with the red one, which can be polysilicon, for example. And then we deposit oxide, yes. This is an oxide, silicon oxide layer. So why polysilicon and then why silicon oxide? The thing is that you need selectivity in etching. So if you want to remove your sacrificial layer, you have to choose it in a way that when you are etching it, you are not also etching your device layer. You cannot use polysilicon and silicon, because if you etch polysilicon, you are also going to etch your silicon. But silicon oxide and polysilicon is very easy. For example, with xenon fluoride, the gas, you can etch silicon without touching silicon oxide. Or, for example, vice versa as well. So with HF, you can etch silicon oxide and not touching your polysilicon. So that's how we choose a sacrificial layer. So sacrificial layer can be anything. Can be metal, can be polymer. Sorry. So then there is like a notch here you will see why it's useful. So they make this notch for just etching, like dry etching probably. And then they deposit another polysilicon layer, so a thick one here, and then they pattern it. So again, dry etching can be done. So again, we cover a silicon oxide as masking, and then open the masking to pattern the underneath layer, and we deposit our basically shaft here. In this case, we remove our sacrificial layer. So which is basically the purple color and the orange one. So we first remove the purple color, and then we can access to the orange one. We remove it. So this oxide layer will be removed, and polysilicon is floating. So you will see this notch was useful to give a touch, basically from the rotor to the substrate. So the rotor is not going to touch completely the substrate. So it's standing on this notch, which is very stupid, of course. Because when you are rotating your motor, then this notch, this basically needle, is always in contact. I even don't know why they made it. Afterwards, so I think I jumped from here. I have to continue like this. Yeah, but anyway, I explained it already. So yeah. And you will see that when you're working, the lifetime is 3 minutes. After 3 minutes, it's completely damaged, this device, which is also very old. But it's very fast. Look, 6,000 RP, like round per second. But it's completely useless. The message here is that MEMS is not very well suited for rotating structures. I don't agree with this, because recently there are like new technologies that we levitate the structures. So basically, there are like carbon layers. One of the students from China was here a few months ago, was working on this. So one of the solutions is that you make a carbon and underneath a magnetic layer, and then the carbon levitates, so it's always in the air. And then you do this rotating structure, so no touching. The other solution is that you make two layers, so bottom and top, and then you apply an electrostatic force, so the gap should be very small in the range of few hundred nanometers. And the motor starts floating because of the electrostatic force, and then you rotate it. So no touching. They work very well, but still they are not like commercialized, still in the research phase, but very nice devices. So MEMS is suitable for rotating structures, but not with this old technique, of course. This is another example of surface micromachining. I think this is a gyroscope, or no, I think it's an accelerometer because of these comb structures. This comb structure, and this is like a spring which is floating, and all of these combs are also floating. And there should be a hinge somewhere. I think this is the hinge, these 2 points. And when you, for example, move it, this spring like start rattling, and then the comb are like going inside, and then the capacitance is changed, and you can measure how much basically acceleration you have. This is also a magnified image of this comb structure. The same idea. So here you can see the comb structure. This is a gyroscope actually. For a gyroscope, I hope you know how does it work. So in a gyroscope, we constantly actuate it. So in a real gyroscope, you need a device which is rotating. It's completely rotating, and when you move it, this rotation is transferred to linear movement, and then you can see how much basically you are rotating somehow. But in MEMS, you cannot rotate. You move it, you vibrate it. You vibrate it, and then when you apply, let's say, movement, it starts again wobbling, and then you can measure the capacitance. So the capacitance again can be measured by these comb structures. This is on the slide, yeah, please.
Can we go more in depth to the gyroscopes and MEMS?
Yeah, my expertise is not gyroscope, but in which sense you want to move?
Like I didn't really completely get how it works again.
Okay, yeah. So gyroscope. To be honest, my knowledge gyroscope is not that much to explain more. But you know that, did you see these old-fashioned gyroscopes that you manually rotate it, and when you change the position, it still stabilizes itself and stuff like this? No? So basically there is a force, it's called...
Centripetal force.
Sorry?
Centripetal force.
Yeah, here you are. That gives you basically the possibility that your rotating structure stabilize when you apply a force to it, so it reacts inversely. But this is also true when something is vibrating constantly. It's exactly the same physics behind it. In MEMS we do like this. So for example, in this picture, probably two of these guys, of these combs, are for actuating, to vibrate these guys constantly. So it's a power consuming device. So you constantly vibrate it, and then by other guys you can measure it. There are different architectures, but I don't know them by heart. But all of them are based on capacitance measurement, the capacitor.
So it's constantly vibrating the structure, and whenever rotational...
whenever external force is applied, then the whole structure starts wobbling. Yeah, I could find a video for you, but I didn't know that I have to go to details of gyroscope, basically, because it's not in the context. Slides is just fabrication. But if you want, I can ask Professor Kraft to prepare a video.
I can look it up.
Yeah, okay. This is, I think, the fabrication of the motor, but I went through more details. Because this is not, for example, explained how the motor is staying on the substrate and stuff like this. But again, very simple. So you have a sacrificial layer, yes, and then you have your device layer, which is polysilicon, And then again you deposit your sacrificial layer, and then here you put your basically shaft. So the shaft is in contact with the substrate, and then you remove your sacrificial layer, and then this is floating, so you just fall down. It's not as simple as this, of course, but the concept is like this. With surface micromachining, we can also do crazy stuff. So this is a wobble motor. I'm not sure what's the application, but like micrometers can be one of its applications. But what is wobble motor? I go to this slide, which is more clear first. So in this slide, you see that this structure is like floating somehow, which I will explain how. But it doesn't rotate. When you apply a voltage, for example, to this electrode, it attracts it because of electrostatic force. So if it is like this, it goes like this. And when you do sequentially, it can be like this. So it doesn't rotate, it just changes the direction. And when you change the direction, you can use it for micrometers to like different angles to guide the light, for example, for different angles. It can be one of the applications. Of course, it has other applications. How do we make it? So we would like to make such a structure that our basically, let's say, rotor is inside it, and it cannot come outside. But how do we make it? So we deposit our masking layers. It can be metal, whatever. We make an opening, and then we etch silicone. This is some kind of bulk micromachining or mixture of both, to be honest. Because here you are etching substrate, and you etch it isotropically. It's very important. You don't want to etch it anisotropically, so you etch it isotropically. For example, with dry etching, with SF6, it's possible. SF6 etch silicon isotropically. You etch it isotropically to have this, let's say, hemispherical shape, and then you deposit your sacrificial layer. Here, after this, you deposit your sacrificial layer uniformly. So this is a tricky part of this fabrication, I would say, because you would like your sacrificial layer to even cover these edges. How do we do this? Electroplating. Electroplating is for metals. You know, for electroplating, there are two problems in this. First, you need a layer that starts the electroplating process. So where is that layer? Second is that electroplating goes to very thicknesses really fast. So it's very difficult to control the thickness in these dimensions. The electroplating is not very good solution. So I would say CVD, gas phase, or let's say like vapor phase deposition. It can be plasma or it can be low pressure CVD. CVD is more or less uniform. Depends what kind of CVD you use, and let's say how do you control the pressure of the CVD. It can be uniform. It can be conformal, we call it. So by CVD, probably here they deposit oxide layer, and then they deposit their motor. Here we can use electroplating because it's quite thick. Also, other techniques is possible. Evaporation, for example, evaporation is a technique that, let's say you want to deposit aluminum. You just heat it up, it evaporates, it comes to your comes on your substrate, cool down, and then you have aluminum. It's very fast, easy, cheap process, but low quality, of course, of material. So it's not explained how they deposit this layer, but there are several solutions, like evaporation, like electroplating, or it can be even a polymer deposition. For example, it can be, I will explain, thick polymers such as SU8. So then when they do this, I'm not sure if it's clear enough, but this black material is in contact of everything in this hole. And then you start etching your sacrificial layer, your silicon oxide, for example. And then this becomes floating, but it cannot come outside anymore. And then the rest is easy. So just you have your electrodes, and then you can actuate it, play with it. Nice. One question, but I will ask it also later. Let's see if it is. Yeah, it's nice to ask it here. Why do we need these guys here? These lines. Why do we need them?
Are we etching using wet etching?
Hmm?
I mean, if we're using wet etching, we're gonna need these
Why?
moves in order to penetrate the structure.
Exactly. So we need to penetrate that. So either wet etching or dry etching. It doesn't matter. It's very important because sometimes, most of the time, let's say your sacrificial layer is going to be etched isotropically, and sometimes you have that material, silicon oxide or whatever, somewhere else, and you don't want to damage it. So you have a small opening. But if your opening is very small and takes a really long time, then your gas or liquid can also damage that silicon oxide somewhere else, which we don't want. So we make it to facilitate the process, the etching process. And this is the image of it. It's published in IEEE MEMS conference, famous one for us. Yeah.
Excuse me?
Yeah.
In the previous slide, yeah, this one. So after we managed to put the full structure in place, and then we etched the sacrificial layer, right?
Mm-hmm.
So there is a part of the device itself of the motor that was etched at the bottom.
Mm-hmm.
How do we manage to just etch the bottom without doing anything? This part.
Let's go to this slide. This?
Yeah, this is the sacrificial layer, right?
This is the light one.
Yes.
Okay?
On top of it, we deposit our motor or the
Our, let's say, active layer.
the active layer, yeah. But after depositing the active layer, we then remove the sacrificial layer,
Mm.
and we also take part of the bottom part of the active layer.
No, you
No.
don't take it, no.
Because
The active-
in number F, it's in contact with the substrate. Number F, the one on top. Yeah, this one. It's in contact with the substrate, and after that it's elevated.
It's not really elevated, it's just comes down. It just fall down. So imagine that your active layer is here, and you etch this light material, silicon oxide, it just fall on this black one. So here I would like to explain a bit about silicon itself. So silicon and polysilicon, which one for active material? Silicon, you know that if it is crystalline, the properties is isotropic. So what does it mean? You know it probably. The properties depends to the crystal orientation. For example, the Young modulus. If you see the silicon, the Young modulus from the top is different from like the side when you are looking at it. So the mechanical properties are different, and you have to take into account the orientation of the crystal of your silicon crystal. But if you use polysilicon, it's not the case. So polysilicon consists of a lot of grains, and each of them has different crystal orientation. And in average, it just behaves as a material which is isotropic. And all parameters are defined as one number, one number as Young modulus and stuff like this. But it also gives us an advantage, because by thermal process you can restructure these grains, the boundary of these grains, and it allows you to engineering the stress, residual stress, which is very important in MEMS. I think you are familiar with the concept of residual stress, right? So basically when you deposit the material, the residual stress can basically appear. But what does it mean? We have two kinds of residual stress. So stress in general means that there is an external force on the material, in the thin film. So residual stress is that this force exists by itself inside the material, exactly when you deposit it. So how does it exist? Two different ways. The first way is that you deposit your material on top of a substrate, and they have different thermal coefficients. Because they have different thermal coefficients during the deposition, probably you go to a higher temperature. For example, in CVD, you go to 500 degrees. One of them expand more, one of them expand less. When they are at that temperature, everything is stable. But when you cool it down, one of them wants to cool, like shrink more, one of them no. So one of them is applying force to other, and the other one wants to expand. So this is residual stress. So for example, if the substrate are applying force to this layer, we call it compressive stress. But if the substrate are like trying to expand it, to stretch it, we call it tension. We call it I came out of my mind. Tensile stress, exactly. So it's tensile stress. So this is one way of making the stress, but the other way is just because of these grains and the boundary of the grains. So they are arranged in a way that the atoms of the material itself apply force to itself, and even alone itself it has a stress. So you can engineer this second one. This first one possibly is difficult to change it. So to solve the problem of the first kind of stress, which comes from the thermal coefficient and stuff like this, you have to make a way, try a solution to deposit your material as low temperature as possible. This is a big challenge in MEMS. But for the second one, you can apply a thermal process. For example, for an LPCVD growth polysilicon, there are such a graph that if you, for example, apply after deposition, you put your sample in oven at 600 degrees for like 120 minutes, and then you will see that after that, when you cool it down, the stress is zero. Or other stuff. For example, if you apply it at relatively high temperature, between 7 to 1000, then you will see that you have, from compressive, you have tensile stress. And also, they found it that at 1550 Celsius, then the stress goes to zero, almost zero, very fast after 30 minutes. Of course, it's not as easy as this. Stress engineering is very complex, and you need to tune it, and machine to machine is different. So if you deposit your whatever material with this machine, then you cannot do same engineering, stress engineering, than you deposit it with other machine. But why stress is important? Because stress makes problem for you. For example, if I deposit a layer on top of this guy, and one of them is like compressive, the other one tensile, when you cool it down, it bends this direction or that direction. It bothers you. You don't like such a thing. There's no extra explanation on the stress. We will come back to it very shortly, but if you have questions, you can ask. I can give you more information. That's it from these slides. The other problem of surface macromachining, so one of them was this residual stress that you have to control. Otherwise, your floating structure can bend or whatever can happen. You don't like it. The second problem is that if you have a step like this, then when you apply your second layer on top, for example, your sacrificial layer, or let's say this is your sacrificial layer, or you want to apply a device layer and then etch this layer. Anyway, you don't want such a thing, because if you remove your sacrificial layer, everything is gone. You want such a thing, basically, your ideal case. But this is very difficult. This is not easy to make it. It depends how you deposit your second layer. So there are different kind of deposition techniques, like spin coating. The spin coating, the advantage of the spin coating is that it's very cheap. You can do it at room temperature. Conformality, very bad. So you will have such thing. And the deposition rate a lot. So you can go to a few tens of micrometers in a minute. It depends how viscous is your liquid. If it is very viscous, you can have a few tens of micrometers. Oxidation. Oxidation is slow. For example, silicon. You put silicon in oven. With oxygen atmosphere, it will be oxidized. You have silicon oxide. So temperature of deposition very high, is around 1100 degrees. Conformality very good. So evaporation, as I explained, evaporation again is very cheap process. So yeah, the rate is in between. It's not very bad, it's not very good. The temperature is low. The temperature of your substrate, of course. The temperature of your material, basically your target, we call it target, that you're heating up is high because you have to evaporate it. And the conformality, yeah, not that good. The sputtering, so are you familiar with the sputtering? Of course. Okay. So it said conformality is not bad or good, but in all of these techniques you can optimize it. But how? Just to give an idea about the sputtering, for example. The sputtering is that you put your target, whatever material, polysilicon, there, your substrate is on top, or vice versa, doesn't matter. And then you start the sputtering. So all of these atoms, like basically the argon in the plasma, are attacking your target, and then these materials are like directly with a very straight direction going to your substrate. If you tilt your substrate a bit and then start rotating it from this center, then you can have a very good conformality. Very easy, which we do it basically. Because the sputtering is very easy process. It's not extremely cheap, but it's very easy. That's why I would say conformality is like plus here. LPCVD, conformality, it's quite obvious because in gas phase, temperature high. This is low pressure CVD. If you go to PECVD, which is plasma enhanced CVD, you activate your gases, your precursors. Instead of high temperature, you activate them with plasma. So basically, you are reducing temperature. For example, with plasma enhanced CVD, you can deposit material at 200 degrees instead of 500 to 700 degrees. 200 degrees is more than enough. It's very good temperature, basically. It's CMOS compatible. If you put your chip in oven 200 degrees, it shouldn't break. So here's a list of different materials. Of course, not limited to this, but to give you an idea of the structure films or active layers, I would say, and sacrificial layers. For example, if you use polysilicon, you can use silicon oxide or PSG. PSG is like a phosphosilicate glass. It's a kind of glass, basically. You can use these two materials as a sacrificial layer because you have selectivity in etching between oxides and silicon. Silicon nitride, the same. Silicon oxide, you have selectivity to silicon nitride. You can etch it, for example, with HF. Electroplated nickel, copper, resist. Normally, photoresist or any kind of polymers is good for metals, even silicon or polysilicon, because you can easily remove them. Not all of them, but most of them, especially all kind of photoresist, you can remove them with acetone, for example, or with EPA. These are like solvents, very well known between ladies, especially. Aluminum, again, photoresist, as I said, so it's very compatible with metals and oxide. Post-CMOS processing. Gold, copper, resist, pyroline. Pyroline is a kind of polymer, is basically plastic, like liquid. You put it, spin coat it, you put it on your substrate, spin coat it, and then you put it in the oven. The solvent evaporate, and then you have a basically dense plastic. But pyroline is different from photoresist, so it's not going to be etched by acetone or any other kind of simple, let's say, solvents. SU8, as I mentioned before, SU8 is a polymer which is viscous and it's very good for thick material depositions. For example, that black structure that I was mentioning can be SU8. It's very useful in MEMS because you can do lithography on it. It's sensitive to UV and it's thick, So it can go up to a few hundred micrometers. It's really, really thick, very cheap process, but very tough. Young module is very hard, you can break it. When you cure it, basically curing means you put it in the oven. When you cure it, it becomes very hard and extremely difficult to remove it, almost impossible. That's why you can almost use any kind of metal layers as a sacrificial layer. And just keep in mind that platinum and gold, I would say, it's very difficult to etch. Any kind of material, any kind of solution that etch platinum, etch everything else. So you cannot see gold or platinum in this layer, in this sacrificial part, because you cannot selectively etch it. Copper resist. But there are, you cannot rely on this table, in my idea, because there are hundreds of material that you can use, and then you have to choose a sacrificial layer based on your process. It's a thing that that you will meet during the fabrication process, basically during the design part. But you have to just keep in mind that sacrificial layer and the device layer, we call it a structural film, they need to have selectivity in etching. Again, so yeah, this is a good table because it also gives you etchants. For example, buffer HF for oxide, very good selectivity, almost excellent selectivity between these two. KUH, I don't like it. It can etch silicon or polysilicon just in a second. You put it there, it's gone. I was doing an experiment with a wafer. I had silicon nitride on top. I was thinking, yeah, look, here is silicon nitride. Huh. Such a coincidence. I was thinking, yeah, my silicon nitride is very nice. So I put it in KUH. I came back 1 hour later to see my nice anisotropic etching, but everything was gone. So everything disappeared in the solution. KUH is very aggressive, also dangerous. Another etchant is TMAH, exactly like KUH. TMAH is extremely dangerous. It can kill you. You have to be very careful. We don't use it as much as possible. Of course, we have it in the lab, but it's extremely dangerous. It's as dangerous as HF. You know that how HF is dangerous as well. If you have like 1 droplet on your skin, then you have to go to the hospital. Otherwise, your mercury level of your blood can increase, and then you will die in a week. Painless. But what happened to my structure, the silicon nitride etched in KUH? Basically, KUH, excuse me, I don't give any pause, so we can continue. I can finish a bit sooner. KUH is like a liquid, can penetrate through pinholes of the material. So if your material is a little low quality, not even highly low quality, a little, it has pinholes or it has cracks or whatever, KUH can penetrate through it and then start etching aggressively, because you know that if your opening is not defined very well, then KUH etch basically silicon in an isotropic way. You remember this? For example, if I have a square, of silicon, and then I etch it, so it's exposed to KUH. At the very beginning phase, the crystal orientation is defined, but when it etches it becomes like this, and many other crystal orientations are defined, are like showing up. And then KUH start etching all of them again and again and again, and then you will see nothing. So it's like somehow isotropic. So you don't want any pinholes. If your silicon nitride or silicon oxide is very well defined, high quality, CVD, possibly not plasma, because high temperature CVD is better than plasma, then KUH works, of course. There are other techniques to protect your sample against KUH. I think you know it. You put your wafer in a clamp, and the clamp is like covering the front side that you have active elements on it. So basically you screw it completely, your wafer is in pressure, in this clamp, and then KOH cannot even reach to the front side, so it's not going to be damaged. Yeah, but it's not very active area of MEMS anymore. We use deep reactive ion etching instead of KOH and stuff like this. Unless we are very poor and we don't have deep reactive ion etching machine and stuff like this. So aluminum, photoresist, acetone, as I told you. The problem of acetone is that acetone is very volatile. It's like evaporates immediately. So you know it. If you want to remove your nail color, if you put pure acetone, after a few days, let's say, your nail is also gone. But yeah, here is written acetone, although I don't recommend it. There are other solvents which are like alcohol-based solvents. They don't evaporate very fast, and then they don't damage also your solution. The problem of acetone is that when you remove your polymer, whatever, for example, your photoresist, it evaporates very fast, and then it remains a lot of residuals. And then there's the small guys on your substrate is almost impossible to remove because they are very small, and they have wonderful forces between your substrate. So acetone is not recommended. Oxygen plasma is excellent. It's very good. Polyimide, copper, okay, etch it. Ferric chloride, titanium, gold. What? Gold. Seriously, no, it's not going to work. Just remove it from your slides. If it works, we use it. It's not going to work. Polysilicon, xenon fluoride, extremely dangerous gas, kills you immediately.
Professor, the structural material is also titanium, so it could be possible.
What? Sorry?
The structural material there is titanium, so on top of that,
Yeah.
gold can be suitable. Because relatively it matters, right? Not the absolute.
Yeah, I know. I'm not sure. As I told you, gold and platinum are very difficult. Especially platinum is very difficult to etch. Only one solution can remove it completely, but that's very aggressive. So I'm not sure. For example, ammonium iodide maybe doesn't etch titanium, maybe, which I'm quite sure it etches it, but maybe with a slower rate. But it will etch many other things. So you don't have only titanium or gold in your substrate. You have several other things, which normally is not very practical to use gold or especially platinum. Platinum is very hard. Even with dry etching, it's difficult to etch it. I would say when we want to pattern platinum, we use lift-off. You know, you're familiar with lift-off, right? No? How possible? You know etching stuff, patterning? Lift-off is very simple.
Yeah.
You don't do etching. You have your substrate. You want to make a pattern of platinum that you cannot etch. How do you make it? You make your photoresist, but inverse. For example, you want to at the end you want to have something like this. So this is the cross-section image. At top it looks like a track, and this is your substrate. The top view, cross-section. You want to have such a thing. So with lift-off process, you make your photoresist, and when so it's one layer of photoresist. I don't draw it, and you apply a second photoresist on top. So we have two layers, and then we pattern it, and then it looks like this. Okay, it looks like this. So it's the first photoresist, second photoresist. We pattern it with lithography, very simple, and then we deposit our platinum. Platinum is everywhere, also here. But because of this gap here, platinum is not going here. So it's only here and here. And then you put this structure in solvent, and then this layer is very sensitive to that solvent, and then it just peeled off. Then you have this. This is how we work with this. Is called lift-off. It's how we work with platinum and gold as well. Okay. Here you are. A very practical example of surface micromachining. This is a coil which is floating. Why do we make it? Why do we? Are we stupid to make such?
No, it's to reduce the inductive fatigue.
No. Ah, you are near.
Because the substrate is glossy. So the founders we are in the substrate gradually.
Yeah, basically to remove the parasitic capacitance of this inductor. Because now it's floating, even if it is vacuum, it's much better than air. Then you have almost no parasitic capacitance. But this is a way to make extremely high quality inductance and stuff like this. Actually, MEMS is used a lot in RF. We have a lot of RF MEMS. I would promise you, you have more than 10 elements MEMS in your phones. There's like a technique called surface acoustic wave. It's for filtering. So basically, you filter very high frequency stuff with ultrasound. So ultrasound, so the wave is coming to your electrodes. The electrical signal is coming to your electrodes, and because of the structure and we have stuff like this, you have ultrasound wave through the lattice of the material, which is traveling through the lattice, and it will be filtered mechanically. And this is used because it's very high, extremely high Q factor. It's very high quality filtering. You cannot have it with electrical components. This is another example of MEMS in RF. RF switch also. So you make with surface micromachining, you make a floating structure, and when you basically apply electrostatic force, this floating structure is stacked like this, and then you activate the activated switch. It works very well and it's used. For example, for such a guy, the problem is that you cannot go to very high frequencies because it's mechanic, but it works in the specific applications. Okay. Yeah, another example from an American institute, famous one, NI, I think it was from NI. And it's just like moving gears, and this is a video. See stuff. Look here, we are actuating with electrostatic force. We are actuating tick tick tick, and then these gears start like moving. Don't ask details. It's not my work. I didn't even read the paper. But I know that that's electrostatic force on top. These are like surface micromachining. Probably is SU8, because if you look at the dimensions, you can see that this line is 10 micrometers. So the thickness is more than 5 micrometers, which is quite thick. And with metal stuff, CVD, spot ring, 5 micrometer is very thick. But with SU8, it's nothing. It's really thin. So it's another video, a bit faster. The insect is rotating. Look, fun, huh? Of course, American people, they have to advertise things like this. Fully integrated surface micromachining. So this is the thing that I would like to insist on. Surface micromachining is a very cheap technique and very useful because you can easily apply it on CMOS chip. So you buy your CMOS chip and then you apply surface micromachining on it, so you do process, because you don't do anything with the software. The software can be this table, can be that silicon chip. So it's very easy to integrate things together. Actually, we are doing this kind of stuff. And there are products that you even don't know in your phone also. There are two ways of doing so. One way is that you do CMOS, which is the only way explained in your slides. You do CMOS next to MEMS. So you buy your die from TSMC, for example, and then you make it a bit bigger, so you have to pay for it, of course. And then you put it in the lab and use process surface micromachining here. This is not a good example because they already etch it with probably KU edge or something like that, because you can see that the substrate is pattern is etched. So it's not pure surface micromachining. But anyway, that's not very important, let's say. So I will go to this slide. There's no animation to show you how does it work. So basically they apply their structure, so again similar stuff that I explained, yes. So the green one is sacrificial layer, this is your active element, electrical access, I would say, to your electrodes. And then you have this gray material which is oxide, like silicon oxide, and then you planarize it with CMP, chemical and mechanical polishing. So you make it flat, and then again you pattern it, so you deposit another sacrificial layer or any kind of isolation layer, and then you pattern it, and then you give access from your MEMS to your CMOS. Very nice, very compact. You cannot do it on PCB. And then you remove, so you pattern your isolation layer, your masking, you remove your sacrificial layer, so your silicon oxide and the sacrificial layer, and then you have your MEMS here. So this is not the only way of making it. As I told you, there is a better way, like more advanced way, let's say, that we don't do it next to the CMOS, we do it on top of CMOS. So it's very good for highly intense elements. For example, the best example is image sensors. Image sensors, there are a lot of lenses, that each of them is connected to an LED. How do we do that? There are millions of lenses, million megapixel, whatever you have it on your phone. But how do we do that? On top. So we make our CMOS, we have millions, whatever, diodes, and then we put surface micromachining, we put our MEMS there, we make the metal layers, layer on top, and we are not going to damage everything because we try to keep everything at low temperature. This is an example of Samsung chip that many of you may have it, it's patented. So you can see that this is a control ASIC, very advanced. Even the controlling unit, not only diodes, because in your camera only diodes are there, and then the rest are like raw column addressing to your controlling FPGA stuff. But in phone, in Samsung for the first time demonstrate this ASIC, on top of it like your diodes and then metal layers, and then here there are lenses and stuff. There are no movement, but I would say fabrication of this guy at top is kind of MEMS basically. It's extremely nice. With this technique they can make 70, 100 megapixel in your phone. But I just bring this slide, this picture, because I would like to let you know that MEMS and CMOS is not limited to surface micromachining. This is a bulk micromachining structure. It's like, for example, deep reactive ion etching floating structure here, that the whole wafer is bonded to the CMOS chip. It's difficult. It's difficult, but it's doable. Because if this is the top side of your wafer, then how do you want to metallize and stuff like this? Yes, you have a question?
Yeah, but I was thinking, okay, well, my question is basically, what is so necessary to have like this? Is this what they call in wafer packaging?
No. The wafer packaging is different story. Why is necessary? To keep the price low, to make it compact.
But isn't it cheaper to have like different, like the MEMS in a different wafer and the CMOS in a different wafer and connect them in a PCB?
Yeah, you have to see what's the application basically. Sometimes it's cheaper. Sometimes you don't take care of the price that much, because if you do mass production, the price automatically goes down, but you take care of the dimension. For example, for image sensor, there is no other way. You have millions of lenses that should access to diodes, and each lens, each diode. There is no other way. How do you want to do this? That's the only solution. And also other techniques. Like, for example, the thing that I'm working on it is like exactly same story, but with medical imaging. So a thing that you do it with your doctor for baby checking, stuff like this. So it's like ultrasound, exactly like lenses. We have millions of them. Not millions, let's say thousands of them. Each of them is connected to an amplifier and receiver. We need access to each of them. So that's the only solution, let's say. Yeah, the price goes down automatically, but it depends on application. But sometimes there are also another solution, another reasons. I don't know. For example, here, let's say, I even don't know the application, but let's say you have an optical sensor here coming from your CMOS that would like to measure a vibration of your bulk stuff on top. So you have to put it on top. You don't need any electrical connection. Maybe you can make electrical connection by wire bonding from here, but you need to make it on top of your CMOS. So that can be a solution. Anyway, so this is a real example. This is like several sensors in one chip: accelerometer, gyroscope, resonant force sensor, IQ filters that I talked, clocks and stuff. Everything like in one chip. This is another example of inductor coils. So nickel bridge, copper bridge, and is also surface micromachining, but very thick. So these are metal, so by sure they are electroplated, because this is an old paper. There are new technologies, but at that time electroplating was the only solution. Not any specific thing to discuss either. Yeah, so there are like advantages and disadvantages of surface micromachining. Okay. So in general, as I said, removing the sacrificial layer is difficult. It can be difficult. You have to be very, you have to be careful of your design and stuff. Otherwise, you have to redo everything. But one of the biggest problems of surface micromachining is stiction, because you know that if your glass of water is wet and you put it on the table, on the desk, sometimes if here is wet, you cannot remove it anymore easily. It's called stiction. Stiction. This is what I mean by stiction. For example, that motor that I saw, I'm really wondering how does it work, because a very small humidity can make a stiction. So maybe that pins there is just to prevent a stiction. So, but what is this exactly? So this is a stiction. These guys are not stick to the substrate, but these guys, yes. When they stick, I will explain you why it happens. But when they stick, you cannot remove it anymore. Van der Waals process is killed through the layer. So this is a big problem, and it still is a challenge, because you can fabricate it. After fabrication is fine. During working, they stick. And it's still a challenge of surface micromachining. So they can put it in vacuum and stuff like this to avoid humidity. But why it happens? Because when you start releasing your structure in a liquid base, let's say solvent, etchant, then because of capillary force and surface tension of the liquid, and at some point you have to dry your liquid, get rid of it. When you start drying your liquid, because of surface tension, this liquid start pulling your structure, and bang, it sticks. And you can see here in this image, half of them, sorry, I have it. Half of them are sticked, and half of the structure are free or fine. So this happens, it's a big problem. But how do we get rid of it? So the very well-known technique is critical point drying. So to explain the technique, we have three phases of material: solid, liquid, vapor. But there is also another region in the phase diagram which calls supercritical fluid, basically, which is not liquid and it's not even gas. It's something in between. Basically, it has both characteristics of liquid and gas, and you cannot distinguish between them. The density of both are the same. We cannot distinguish. So the solution is that we apply a liquid in our MEMS structure. For example, you etch it with acetone, let's say EPA, whatever, and then you substitute a new liquid. You don't make any air, so no air gap. You just remove that liquid and add a new one very smoothly. And then when your new kind of liquid is there, then in the phase diagram you travel like this. So you increase the temperature to go to the supercritical fluid, and then all of a sudden reduce the pressure, then it's gas. and then reduce the temperature. Is gas, and then all of a sudden is gas. It's like basically the structure doesn't see any capillary force or surface tension. For example, liquid CO2 is used a lot, and yeah, it's a very simple process. We add liquid CO2 to the machine. It's a small chamber. It has a window like this. It has a liquid, so this is liquid CO2, and then when we increase it, so it's in high pressure. When we increase the temperature a bit, like few degrees, it goes to supercritical fluid, which looks like this, and then all of a sudden it's gone, bang, and then you get rid of stiction and stuff like this. But stiction, as I told you, may happen again because of the humidity of the air, sensitivity of your device, and stuff like this. So these are two machines that exist. Many other machines exist actually. Ours is not similar to these guys. That can do critical point drying. Very simple machine, is small, like this dimension. So the other solution to get rid of stiction is this, basically, this structure. So in your sacrificial layer, you make these bumps, and then when you deposit your device layer, it has these guys. Because of surface tension, when you are evaporating your liquid, only this part is thick, which is very small and doesn't let to have a very big van der Waals forces, big area basically. To be honest, I've never done such a thing, but yeah, these tricks exist. Something like this. Of course, it can affect your process. It can give a bit of extra mass to your resonator, change the resonance frequency, stuff like this. Or for example, during resonance, all the time it can hit the substrate, which gives a lot of like harmonics in your resonance. But you have to be careful. So this is a real example of such a beam that can be used in like application that I have shown. But how do we fabricate it? So just an example. We fabricate such a thing only with 2D layer deposition and etching. Very nice. So we start with a sacrificial layer. We make an opening in the sacrificial layer, and then we deposit our second material. Of course, this picture is after patterning of our second material, or let's say our active layer. So active layer also goes inside. That's why we have this hole, and then it gives, this is more clear. It gives like a touch to the substrate, and then when we remove the sacrificial layer, we have this structure. As I told you, again, this is not as easy as this, and it can be very thin here. So because of like straight deposition and stuff like this. So the more smart solution is that we deposit, we start with our sacrificial layer with no opening, and then we deposit our structure, and then we start etching the sacrificial layer. For example, by reactive ion etching, which is a directed way of dry etching, and we can use even this guy as a mask, and then we can etch it, and we end up with this structure. So again, a floating beam. So these guys, the edge, so basically the stator of the rotor, of the motor, the stator, they can be an example of such a thing. Yes, boss.
Can you go to the previous slide? Yeah, if you use dry reactive etching, how can you etch below the cantilever beam?
We don't. Okay. Yeah, you're right. If you do a dry etching, we cannot etch below the cantilever. That's true. So you have to use a kind of isotropic etching. Yeah, thank you.
But then that would also etch the base, right?
Yeah, but you have to be careful. So that's why this is a bit bigger, and that's why, if you notice, it's a bit smaller. So you have to remove it from the etching on time. Otherwise, yeah, you can also etch that. That's true. Let me think if there is any other solution of this. it depends what is your sacrificial layer. Because if it is, let's say, silicon oxide or even polysilicon, in gas phase etching, plasma etching, it can be isotropic as well. But this should be taken into account, of course. Otherwise, it will be etched away.
Basically, it will be a combination of both isotropic and using a particular mask.
That's possible, yes. Yeah. So SY wafers. Anything else here? Okay. So SY wafers are silicon and insulator wafers. So the definition is that we have. I would refer to this image. We have a silicon substrate, and there is like a thin silicon oxide layer on top of it, and another silicon substrate. All of them are crystalline silicon. This is not polysilicon. Another very, very thin silicon substrate on top of silicon oxide. So this is called SOI, silicon and insulator. It's very useful in MEMS process because the silicon oxide can be used as an etch stop, for example, in deep reactive ion etching, in KOH etching, and many other stuff. So this is very useful. I'm not sure if there is any example. Yeah, okay. So how do we make it? There are two different techniques of making SOI wafer. The first technique is that we start with a normal wafer, we oxidize it. So here we oxidize a normal wafer, and then we bond it, synthetic bonding, for example, we bond this silicon oxide to a second wafer, which is here. And then we start polishing the second wafer. So basically a lot of material are wasted, but it is used in industry. And we start polishing, thinning down, just to our desired value. To give you an idea, this wafer is normal. It can be like 400 to 500 micrometer. The silicon oxide layer can be as thin as 200 nanometer up to few micrometer. 10 micrometer, for example, or even bigger is possible if you pay more, of course. And then the silicon active layer, we also call it active layer. The silicon oxide, we call it box, buried oxide layer. The active layer can also be whatever you want. 500 nanometer up to, whatever, 100 micrometer, it's up to your request. The other technique, which probably is not very useful for very thick active layers, is that we basically diffuse oxygen through the silicon. So we don't use a second wafer. So we diffuse oxygen, make silicon oxide by diffusion, implanting basically. This is a technique that also can be used.
Why is the second technique not used?
Why? Because if your device layer is very thick, then oxygen should be diffused a lot, and it's not possible.
So it's like the active layer would be so thin that it's not useful anymore.
Yeah, I'm not sure how thin, but of course it's not going to be 10 to 50 micrometer. So here I explain it exactly. So this is the second technique by oxygen diffusion implanting. This is the first technique. First technique can be a bit more economical by a technique which was introduced by a French company called Soitec. So basically they do the same. So they oxidize wafer A, the red is the oxidized part. Then they apply hydrogen ions. So they diffuse, they implant hydrogen ions to a certain thickness by their own techniques, of course. And this diffusion causes bubbles, basically make the bonding between silicon atoms very weak. After this, they bond it. So similar to that, they bond to the previous process. They bond it to the second wafer, and then because of this weak, basically bonding of silicons, these bubbles, they can break it easily. And then they can reuse wafer A again. So They can reuse wafer A again, and it's a very useful technique.
How is that cutting happening over there?
I'm not sure how do they do this, because it's, they don't reveal it details. But I think by mechanical force. Yeah, or it can be cutting. For example, if the bonding is already weak, you just trigger it with laser or with saw, you just go until the end because the bonding is already very weak.
Laser should come from the cross section,
Yeah.
not from the top.
I'm not sure, but that's possible. Yes.
How can this be better than just grinding? Because you still waste a lot of material.
No, you don't waste any material. Yeah, so you reuse wafer A again here. Yeah, that's very cheap for them because it's expensive. So that technique you have to use. You have to waste the whole wafer. But this is Soitec only sells big wafers like 8 inch, something like that. That's why it's more economical for them even. So this is an example of SOI fabrication. So this is the active layer. You can see how thick it is. There is no labeling on it. This light one is silicon oxide, and this is a substrate. So they do deep reactive ion etching. You can see the ripples of deep reactive ion etching. You know that ripples happens. You know it, okay. So the ripples are quite obvious, and then they reach to the oxide. There is a small notching. If you notice, small notching. Yeah, bad operators. They reach to the oxide, and then they start etching oxide by HF isotropically. That's why it goes like this. So the oxide is etched by HF. Most of the time it's by HF because it's quite fast, isotropically. And then this guy is floating, so it can be used as a beam, resonator, or any other technique. This can be also done from the backside. For example, what we do in our clean room for our process is that we do deep reactive ion etching through the backside, which is around 300 to 400 micrometer. Basically, depth should be etched, possible. We do it, we reach to the oxide, then we remove the oxide, and then we have a floating membrane. So no hole here, it's floating membrane. Just for your information, because it's very cool, there is other kind of SOI wafer. It's called cavity on SOI wafer. So what they do is that here they do deep reactive ion etching to make small cavities here, for example 50 micrometer, and then they apply oxide on it, and then they bond the second wafer and polish it. Then you already have floating membranes. Very nice process. Then you don't need to do deep reactive ion etching, waste a lot of time, material and stuff. But wafers cost a lot, each 200 to 500 euros. So this is an example of bulk. No, what is this? SOI wafer. Yeah, it's an example of SOI wafer process. So deep reactive. So this is an SOI wafer at the bottom. Deep reactive ion etching were done, and then the oxide is removed. So we have floating structure. And for packaging, as you mentioned, they bond and the second wafer on top. And it's the device, the resonator, whatever is sealed. It can be in vacuum. It's hermetic sealing, we call it. And yeah, the other part also is available. For example, it's a temperature sensor, pressure, whatever that you need to give access to the air. HARM process, high aspect ratio micromachining. So by SOI wafer, you can make high aspect ratio micromachining, quite obvious. And again, they did it. So this is an example, I think, a gyroscope that they did with deep reactive ion etching process. And this technique doesn't have the problem of stiction, the problem of failures, and stuff like this. You don't need to take care of selectivity. So I'm a fan of it quite a lot. So they start etching the device layer, and then they access to the oxide layer, and then they etch the oxide layer, they remove it. And then these guys are floating. So you can choose, for example, your oxide layer quite thick, about 2 to 10 micrometer, that there is no risk of extinction. Yeah, and this is also for the capping. So this is for such a structure. When you make with the SOI wafer, then you oxidize your second wafer, which works as capping, to package it, and then you pattern your oxide to give a small cavity here, and then when you have your cavity, you deposit metal layers, because it was found that if you do bonding with metal layers, so metal to metal, then which is called the eutectic bonding, then you have the best hermetic sealing. So metal to metal, I think there was like a graph, I remember, that metal to metal is hermetic for more than 10 years or something like that. So that's why for hermetic sealing, here they deposit metal. Otherwise you can directly bond this guy to your silicon device. Here in this slide. So this can be done directly to silicon. But metal to metal give you the best hermetic sealing. Yeah, hermetic contact. So this is open, no hermetic, so you can have access, for example, for temperature sensor, pressure sensor, for example, this can be a pressure sensor, and this can be a gyroscope, which you don't need any friction to air and stuff like this. Yeah, this is also another example. Modern SOI fabrication process, 60 micrometer SOI. So the device layer is 60 micrometer, quite thick. The nice thing is that, yeah, when you are removing this 60 micrometer, because it's quite thick, so it doesn't break easily, then you can also etch it with deep reactive ion etching to release the whole chip, MEMS chip. Then you don't need to do dicing. So basically, one step is removed, and then the whole process becomes cheaper. You got the point, basically? No? When you are etching your structure, for example here, when you are etching your structure, let's see if it gives you, here you are, okay. So I go through the fabrication, you will see. So this is an SOI wafer, this is the substrate. They etch the substrate to reach to the oxide layer by deep reactive ion etching. They also etch by deep reactive ion etching the device layer, and then they start removing the oxide layer by HF, for example, etching isotropically. The box layer is removed, and then you will notice, yeah, give an error. So you will notice that it's already, look, it's already etched from the substrate totally. So it's already released. You don't need to dice it anymore. It released by itself because of deep reactive ion etching. So you already did it. So it's not one extra step. You do it because you are doing it. So why not to release the whole chip as well? It doesn't cost at all. So principle of comb drive. So again, comb drive is coming here with SOI as well. So this comb drive is, yeah, this comb structure is for driving, as I said, and these guys works as a spring. So this is the anchor point, this is the anchor point. When you drive it goes like this probably, back and forth, and then the capacitance here can be changed, and you sense it here. So this is a real example of comb drive structure, and you see the holes again, because very clear why do we have holes, because silicon oxide is everywhere, and this is quite big area. So if you don't make these holes and you start etching silicon oxide, then you can etch silicon oxide almost everywhere, and everything is floating, which you don't want it. So you take into account, okay, what is the thickness of my silicon oxide? Because if this is your SOI wafer, this is your substrate, and this is your box layer, and this is your opening. When you start etching it isotropically, your under etching is the same as the thickness, the best case. Because when you want to reach to the end, you're also etching it from this side. So this dot here will be etched first, and it continues when you are continuing going deep. So this same thickness as this guy, as the thickness, it will be etched, and then you have such a structure. So under etching looks like this. It exactly looks like this. And you have to take into account, so the position of the holes should be in a way that you don't have under etching more than what you wanted, for example here, or here, or there, or anywhere else. Okay, yeah, very good. I'm going to finish it. Fabrication techniques, non-silicon materials. So there are more advanced stuff in fabrication, like really 3D stuff, high aspect ratio, quite complex. It's not possible with bulk micromachining or either surface micromachining. Well, how do we do this, basically? There are different techniques which I go through. One of them is Liga. So Liga comes from a German word, which Professor Kraft knows better than me because he's German. Lithography, I'm not sure how they pronounce it in Germany. Lithography. Galvanoformung, which means that you it's such a nice language because just one word means a lot. Electroplating of a suitable metal into high aspect ratio resistance structure. Upforming, so Liga in general. So molding and stuff I will explain. Anyway, so what is Liga? Liga is that you start with your substrate, you deposit a sensitive material to X-ray. Let me see, yes. Sensitive material to X-ray. And then you pattern your material, which is a kind of polymer. Normally they use PMMA. It's plexiglass. I don't know, you know it. Plexiglass is looks like this. It's much stronger, much thicker. It's used in maybe window of like army cars and stuff like this. So plexiglass, they pattern it, and then they electroplate in between, and then they release the electroplated part, and then use the electroplated part as a molding. And then they deposit polymer in this molding several times. So only this part should be done one time, which is quite expensive and difficult. And then you can do the molding for several times process. For example, if you are manufacturing special gear or whatever, then you order the molding to the company who can make it, and then you have the molding, and then you repeat the process. But the problem is that you need X-ray. So apparently to perform lithography stuff here on this material, you need high energy X-ray beams. And it's only possible by X-ray synchrotron, which doesn't exist in many locations. So if you have this, good for you. You can do this. So basically, you accelerate X-ray a lot. So you have a polarized X-ray beam that is like, and then you use, it's a very simplified process, of course. Mirror using grazing incident. So grazing incident means that, simply speaking, it like make the angle of the X-ray very narrow, and then the beams are very like straight and parallel to each other. And then they hit your mask. So the mask is very, very funny because here is silicon. X-ray can pass silicon, but gold can absorb it. It should be thick gold. I'm not sure how thick. And then it goes through your PMA, and then you can pattern it. So to give an example, this is a process. So you deposit Yeah, it's not very complete. Anyway, we go through it fast. So you have your PMA here, your mask with patterns, your radiant X-ray, you pattern your PMA, and then you polymerize it, basically mold, inject polymer into it, and then when it is dry, then you can remove it, and then you have this structure. And you can do reverse also. So, excuse me, I made a mistake. When you make your PMA here, you electroplate in here. So this blue one is metal. You electroplate it, and then you have your mold. So this is your mold, and then you can apply polymer again to it, and then you have your structure. And this can be redo several times, so it can be repeated. But this is the advantage of Liga, because Liga makes something between surface macromachining and bulk macromachining. So is some dimension-wise something in between. So the exact process looks like this. So we start with a metal layer that let us perform the metallization, the electroplating. Then we deposit. Yeah, this is a sacrificial layer. Yeah, okay. And then the metal layer. And then if we have our PMMA, we pattern it by X-ray. We electroplate it. So here is the same material. We electroplate it, fill the holes, very thick, easy. And then we remove our PMMA, and then we remove this guy from the substrate. And then we can reuse this metallic structure several times as molding. So it's called Liga. So this is made by Liga, for example, turbine for whatever application. I have no idea. Other stuff like this. Very fun, huh? But the problem is that when you make these guys, look at the dimension. How do you want to handle it? How do you want to integrate it into the system? It's very difficult. So you need special machines, expensive stuff to integrate it, which is like a disadvantage, or let's say drawback of Liga. Another example, for example, for aligning an optic fire in front of this optical component, they made it by Liga. It's a very fine element. And this guy as well, this is out of metal, so they directly use the mold as a material. I add another thing which I really like it. Do you know what's this? This is the device which in this dimension is going to work instead of centrifuge in uranium enrichment. So basically uranium as a gas is injected to this guy, and the heavy guys goes here, light guys goes here. Very simple and smart. And they use it, so centrifuge is old. Don't use it. Liga, okay. So pros, high aspect ratio, allows fabrication, polymer and other material, nice. But as I said, it's difficult to integrate. It's like single mask structure, complex 3D. Yeah, you cannot really do complex 3D structure as I have shown, like at the beginning, like this spiral shape, stuff like this. So it's like semi 2D. It's a 2D which is like extruded, and it also requires X-ray, which is the most drawback, the most important drawback. But if you are poor like us and you don't have X-ray synchrotron, then you can use a material which doesn't need X-ray, like SU8. SU8 is a very nice material. You can go a few hundred micrometer easily. I think it's difficult to reach millimeter level, but anyway. And you can when it's like sensitive to UV, so you can do lithography by UV, and it's also like it's a negative photoresist. You have to think it. Keep in mind that this is a negative photoresist. And we can have very nice high aspect ratio. Look at this, 10 micrometer, 140, 500 micrometer. So aspect ratio is 14.5. It's very nice stuff we can make with SU8. SU8 is used mostly in micro channel fabrication for how do you call it, lab on chip stuff. So this is an example of SU8 in our clean room. Very nice. It's a bit difficult to tune it, but it's possible. For example, you can see that it's a bit thicker here, and it becomes thinner. So the process should be tuned. This is another example of making needles. So these needles doesn't look very sharp, right? But they are sharp enough to inject, to go to your body, don't worry. SU8 is deposited on silicon wafer, and it's like with a mask, it's exposed to UV, and we can pattern it, we can develop it, and we can easily make structures out of it. The pros of SU8 is like, again, high aspect ratio, very easy fabrications, using polymer in the structures. We can use the standard tools in the clean room. But the disadvantage is that it's very difficult to remove SU8 from your substrate. When you develop it, it's there, almost forever. It's brittle, so if you want to use SU8 for like devices that you need to delaminate from the substrate and like integrate it to other things, as you do it with Liga, SU8 is very fragile, and it's possible easily to be cracked. So that's a disadvantage. Again, like Liga, single mask structure, semi-3D devices can be done. Yeah, this is also a picture of microfluidic microchannels for lab-on-chip applications. So basically, you can realize very fine channels in SU8, and then you can inject liquids and stuff, and yeah, do many other fun things with it. Okay, so let's talk a bit about stress. It's a bit late to talk about, but yeah, to remind you again, if you have a stress in your deposited active layer in surface micromachining, and then you remove your sacrificial layer, then because of the stress, your layer is going to bend upward or downward. You will see. So this is your device, which is like deposited device layer. It has a stress, and you don't know it. And when you remove the sacrificial layer, it looks like this. But you can use it as advantage. So you can use like these guys here, electrical contact. But I'm not a fan of it because the reproducibility is under question mark. Who knows that because of some reasons the stress of the material is exactly the same, that after removing a sacrificial layer you will still have this. So it's not very reliable, in my idea, to use the stress as the main key point of the fabrication process. But it can happen. So this is, I see this as a disadvantage, as a drawback basically. So stress can make this, especially for thin films, for surface micromachining. And it really happens almost all the time. So you have to control the stress very well. Okay. Laser beam CVD. This is a technique to make complex 3D structures, real 3D structures, not semi-3D. So it's CVD, but they apply a laser beam to make the reaction of the atoms, of the gas atoms with the substrate. And then if they change position of the laser, they can basically make any kind of 3D. The concept is exactly the same as 3D printing. The concept is exactly the same. Focus ion beam, a very nice machine. You can deposit, you can etch selectively, locally, very fine, in the range of resolution of nanometer. So basically with the gas nozzle you inject gases and you focus an ion beam, for example gallium ions, you focus it and you make reaction here. And volatile ions also goes away. and then you can make reaction, or you can increase the energy of your gallium and then etch away. For example, here you etch away these guys, and then you can see how it goes by time. It's very nice. You can really see it live in the machine. And if you like focus the beam in another directions, you can really make 3D structures. So you inject gas, and then your focused gallium beam is like changing by time, and then you can have different complex structures. Look at the dimension of this wine glass. The machine is very nice. We have one in ESAT here, just next door. It costs about 1 to 2 million. It's quite big, very big, huge. Yeah, a very quite complex machine. You can make many other things. It's a useful machine for CMOS application. For example, people here, they make IC. They are listening to music, whatever, they don't focus, and they make mistake. And then when the IC comes from TSMC, it's too late. And you put your IC under this FIP, and then you etch the mistake part, and then you access the underneath layers, and then you deposit again metal layers. You can deposit several metal layers, like platinum can be deposited, for example. Tungsten is very common one that can be deposited, but not all of them, because the precursor, the gas precursor, is not available. There's a special precursor, stuff like this. Anyway, so the other technique to make 3D structures in MEMS is this machine. It's called 2-photon lithography. It's very nice when we have it, and you can make these structures very fine. Detail. The resolution is nanometer. Look at the dimension. Look at the details. Just to give you an insight, what can we make? Look at this stuff. I think this is done in our clean room. Look at 200 micrometers. Look at the dimension. Look at details. Oh, motorcycle. This is designed for Professor Pures because he loves motorcycles. He still have it in his office. Yeah, but I don't know where is it because it's very small. I cannot find it. Look at the details. But how does it work? Like in 5 minutes, I will finish my talk. Basically, come back to this slide. You are familiar with UV lithography. For UV lithography, you apply UV, like we call it float exposure. UV everywhere is like on your photoresist. You give a bit of energy by a specific wavelength to it. And because of that wavelength, the energy is enough to cross-link or decross-link the photoresist. I mean by cross-linking, I mean, for example, if you have photoresist, you deposit UV, and it cross-link, and then when you develop it, that part stay there. This means cross-link. Decross-link is the inverse. So when you develop it, it's gone. So negative photoresist, positive photoresist. But if you reduce the energy, basically you increase the wavelength, you reduce the frequency of the wave, of the light, then you don't have enough energy. But if you focus that basically low energy beam, if you focus it, then there is a probability that 2 photons are colliding each other. So there is a probability. And if 2 photons are colliding each other and you reduce the energy by half, then you have same energy at that point specifically. And you have a probability function of energy of the light, which looks like this. And this defines your resolution, which is in the range of nanometer. And if you put your photoresist on top, and then you move it, or move the focus point basically wherever you want, at the end you have a quite complex 3D structure. It's a very simple idea behind it. So another technique is electroplating, which you are familiar with. So you electroplated metals, fast grows, very simple, that's it. So any question? Yeah.
The images that we saw for 2-photon lithography, what is that? Is that the photoresist? Or
This is a photoresist, yes.
So that is a photoresist.
No. Basically, when you make this motorcycle,
Okay.
it's in a block of photoresist. But when you develop it, everything is gone, and then you only have your photoresist, the developed part.
Okay. So, but what is that made of? Like, what is the material?
This photoresist is a special kind of photoresist. It has an industrial name.
Okay.
Yeah. And I'd like to talk a bit about your exercise session. Just give you what's the concept. So you have to make groups of 3 people, and then you choose, each group choose 1 paper out of 50 papers that we prepare for you. So the papers are fixed, so they are like publications that we give to you, and you cannot choose your own publication. You choose 1 publication, every group of 3 members, and then in a specific day, you come and present that. Basically, you have to also give an idea how to enhance and how to make the drawbacks of the paper better. And it's mandatory that everyone give a talk about 5 minutes, 3 to 5 minutes, something like that. And if someone is absent, the score is 0 by sure. We will give a session, so you only have 1 exercise session out of the exercise stations that you have it, that we explain the papers, the 50 papers, we just give like a summary out of them. And then we will see you again in December, somewhere like 11 and 12 December. And we also announce you through Toledo about groups, about timing. You can choose a specific time whenever you want and stuff like this. No, I think time is not, we choose for you. Yeah, we choose for you. But groups, think about groups, because sometimes it happens that a person doesn't have any groups. So think about it now, group of 3, preferably, not less.
When do we get to choose the papers?
As soon as possible. You can choose it and
Toledo?
choose the people.
No, paper.
Paper, we will let you know.
Oh.
We will let you know, yeah.